Hey guys, welcome back to this tutorial. This is a second tutorial on power system network design. If you like this tutorial or the previous one, please don't forget to like and share, give it a thumbs up and subscribe to my channel. That will be highly appreciated as we move forward. So in this tutorial, we are going to reduce this network diagram that we've seen previously. Now this is a representation of a network that can be implemented for a country or a city, anything. So this is basically a representation of busbar that represents substation with transmission lines running down the line down to the last distribution center or the last load or consumer. So these are parallel lines. You can see they all rated exactly the same. It's basically two lines running simultaneously. Now we're going to reduce this to a single simple diagram that we can work our calculations. So I emphasize, if you stick around, this is going to be focused on the protection of busbar. These are busbars, so we need to focus on how this busbar can be protected, because you may have a lot of things being connected. For instance, you can see this busbar number 2. We have a load that's connected here. That's an 11 kilovolt system that's going. We have a transformer. We don't know what's going to be connected on this busbar, but we know it's coming from this busbar 2. So we need to ensure that busbar 2 got adequate protection to deal with whatever situation that might occur there. Even though this busbar 2 itself need to have its own protection. So if you stick around, you're going to see various ways of how to make this protection possible in an electrical network design. This is the same process or procedure that are taken before anything is designed, from power station, substation, to transmission line. Okay, so let's see what is the next step for reducing this network. We have now removed the parallel line that was going along with this branch, as you can see, and we've removed the load that were connected on some of these busbars, as we're going to be focusing on the protection of busbar, as we said before. Now you can see this substation here got it's 132 kilovolt. That basically means the generator that we have here is supplying a magnitude potential of 132 kilovolt. But then they say the generator, they have a per unit of 24%. That is important, because this 24% is what's going to tell us with the voltage what exactly is the power that is being delivered. Remember, just like your battery got an internal resistance, the internal impedance or resistance of the battery is what tells you how much power the battery can deliver based on its voltage. So this is basically the same. So the 24% is the internal impedance of the generator. So we're going to see how much power will be coming out of that generator. This number you see here is the maximum short circuit that can flow if there is a short circuit here. Stick around, you'll see how we get that. And there is a 4.5 kilometer line running with a back cable of 650. And we have the same there, a bus bar. Then there is a 80 MVA transformer. And we have another line here. And the 5th bus bar. So it's a 5 bus bar system. Now, look at these cables. Now this cable, they just give enough parameters, like the name of the cable and how long it is and the current rating. But how do we know what cable to put there, what the reference? Because remember, a cable is a wire. It's a wire, and it's a resistance. It must have an internal resistance. There is always going to be an impedance to it. So some clever people have already done the work for us. We don't have to suffer to try to find out what exactly are the parameters of the cable. So we're going to look at this table of reference. Now these are provided by the national standard for electrical system. So we have the name of our cable is Busbar. The name of the cable is Busbar. So we look at a table of reference and bear what are the values we need. So we've got R1 and X1. Now R1 is the resistance, X1 is the reactance. You know the impedance is made of a resistance and a reactance. It's an inductive impedance. Now, and the important thing to know also is these values and references are referenced per kilometer. So if you have 100 kilometer, then you have to multiply it per 100. That's basically how big your impedance is going to be. And that makes sense because a long transmission line is going to be more voltage is going to be dropped on the system, but that's a subject for another day. So that's what we have here. And these were tested, these parameters were tested on a 100 MVA per unit system with a 35-degree ambient. So basically not the typical winter. So if these parameters might change depending on the weather. So those values are for a 35 degrees ambient. So basically summer. So in winter, you should be expecting different parameters. So the values can be changed, might be changing depending on the weather. Okay, so now you know where we got the values. So basically we're going to replace them. And moving on, that's what we do. And what I've done here, I've now replaced the bare cable with the impedance parameter. Now you can see this is a resistive part and this is the inductive part, and that's from the impedance, and we have to multiply it by the number of kilometers. And I've done exactly the same thing here at 4.7 and also here. Now you notice here we have something different. We're going to see, instead of having a name of the cable, we had the millimeter square. Now this is the area of the cable. Now going back at the same table, we can see that they also gave us the area in millimeter square. Now we just have to see which area corresponds to what we have here, which is a 710. And we found that the 662 is close enough, so we take the values from that and then we replace and we get this impedance here. Now when we multiply it, we now get this impedance here. Now these are now the final, this is now the final impedance value for this transmission line, and this one as well, because we've now multiplied it by the number of kilometers. Okay, so we can still simplify this diagram to make it more readable. I mean, you can see it exactly, there's an up and it's going downstream. So we can basically reduce it to something more easily readable. That is something like this. So we got now our one line diagram simplified. As you can see, we still have our 0.24 J, which is the internal impedance, as we've said, of the power station, this power station here. Now we have the impedance for line 1, and this is Busbar 2. This is impedance for line 2, and this is our giant transformer. And this transformer have a per unit old of 10.1%. Now this one is important. These parameters are given on the nameplate of the transformers. Now we're going to need this old per unit as we're going to be changing from whatever base these values were calculated to the new base of 100 MVA. The new base of 100 MVA that we're going to be calculating for our system. And this is bus 4. Now this is a step down transformer that's taking from 132 to 66. And we go to line 3 and then bus 5. Now we're not going to be dealing with this transformer. I've just included them just for illustration purpose. This is a load section. It's going into a load, but we're not going to be worried about that. We only concern on the protection of this bus bar. So each of these bus bars represent a substation, and you know what we found at a substation. At the substations, there are relays, there are current transformer, voltage transformer, line arrestor, and so forth, a lot of things, circuit breakers. So those are the things that you will be focusing and how to calculate and find them. Thank you for watching. Please, if you like this video, give it a thumbs up, and don't forget to subscribe to my channel so that you don't miss the next videos, and also share to your social media network. Thank you very much. Your support is highly appreciated. Thank you.